Hello, my name is Mohammed Rida, and today I will be demonstrating for you the effect of spinning bodies. Here is a prototype of a gyroscope which can spin around the y-axis or x-axis, and we have different objects in question, which is a square, a rectangular rod, and a circular disc. All these objects are assumed to be uniformly dense, and this is from the problem statement. Another assumption is that they are initially at rest within the Earth's reference frame, there is no air drag, and the contact between the axles and the frame is frictionless. To show more about this prototype, you can see here it's connected through these axles, and this is the outer frame connected to the inner frame, which is able to rotate freely around the x-axis. Now, to demonstrate the first object, which is the circular disc, we're gonna give it a little spin, angular velocity, and let's assume that the arrow is facing the camera from this way, and let's see if it'll stay the same place after the spin. And you can see it from this side, but from that side it is seen that it has shifted a little bit. Let's try it again. And you can see the arrow is still facing the camera. Now let's try the square. And here I have the square over here. Let's give it a little spin. Arrow facing the camera again. And let's give it a little spin and see what happens. Just a small change, a very slight deflection from where it was. Let's do it again. Sorry. Let's do it again. And we see just a very small deflection. Okay, and here the last object is the rectangular rod. Okay, and it's you can see the arrow over. Let's do it this way. You can see the arrow from this side over here, facing the camera. And now let's give it a little spin. See what happens. So what happened is, there's a big shift from the arrow going straight from the camera to the arrow being on the other side over here. So we can see that the rectangular rod did spin arbitrarily fast in the Earth's inertial reference frame. And this is mainly because of the moment of inertia, which I will prove soon. Here's an example of a diagram I drew before I built the prototype. And next is the assumptions that I stated at the beginning of the video for this problem. Now, for the circle and square, moments of inertia of a circle is always equal in any direction, since the radius is always constant. For a square, the length is equal to the width, so also Ix will always equal to Iy. Now, for a rectangular rod, the length is not equal to the width, so this will be the main issue why the rod was able to spin arbitrarily to the Earth's inertial frame. And this will be shown with this equation over here, which says that the angular frequency of precession is equal to the torque over the spin angular momentum, where the spin angular momentum is equal to the moment of inertia multiplied by the spin angular frequency. Here we assume that the torque is constant and the spin angular frequency is constant. So what really the angular frequency of precession is affected by is the moment of inertia. And since the moment of inertia of a rod changes from the x direction to the y direction, then this proves why that the rod will spin arbitrarily to the Earth's reference frame, and the circle and the square will not. Thank you for watching, and yep.